all over the world. Sometimes it's difficult to pick up time, but we're doing the best we can.
Yeah, thank you for having me.
Oh, it's our pleasure.
I'm very happy today. Many people and live friends. We start a new academic year, and I think it's good time to turn back to mathematics.
Yes.
All right. So, friends, let me introduce our speaker today. So today we have Dr. Anna Vershynina from the University of Houston. And actually, you know, I know her works from last year, and she has many papers with, you know, with some, I would say, you know, with Carlin, Dr. Carlin, and so on. You know, I read their papers from from all the time. And Dr. Leap, you know, work with inequality, tearing inequalities all the time. So, Anna, thank you very much for your for joining us. So, I think it's your time. Yeah.
All right, thank you very much. Yes, thank you, Ho. Right, so I'm going to talk about different trace functions and their applications in quantum information theory. So we're going to start with quantum relative entropy. I'm going to define what it is. And in particular, the data processing inequality that it has to satisfy. And the data processing inequality, it basically says that quantum relative entropy, which sort of like a measure of difference between two quantum states, of how far apart they are, the data processing inequality says that after the states pass a noisy quantum channel, that distance should be smaller now, because it gets harder to distinguish them. So the smaller the distance, it's harder to distinguish them. So then I'm going to generalize this quantum relative entropy. There are many, many ways to generalize it. But in particular, I'm going to talk about Renyi, sandwiched, alpha Z, and F divergences. And again, all of these generalizations, physically, they should satisfy the data processing inequality. Otherwise, it's not a good definition. So we're going to talk about data processing inequality and the trace functions which they generate. So to prove data processing inequality, we're going to need to prove the convexity of several trace functions. And in particular, the equality case in the data processing inequality is very interesting. And it does says something about the states and the channel. So if the quantum relative entropy does not change after the states pass through the noisy channel, that means actually that this channel is noiseless in respect to these two quantum states. So even though it is a noisy channel for these two states, it acts like a noiseless channel, so we can reverse its action. And I'm going to finish with generalization of these trace functions and where they arise. So let's talk about quantum states first. So the quantum system is given by a probabilistic ensemble of pure states. So this is how I'm going to denote a pure state, which is basically a vector, orthonormal vector in any finite dimensional Hilbert space. So instead of writing the arrow on the top, in quantum information, we write it as a bracket notation. Pj is operability distribution. So the state itself is given by the density matrix or an operator for the system, which is a convex combination of the projections onto this vector. So this is the vector multiplied by its adjoint. So it's going to be a matrix, which is a projection onto that vector. Okay, and mixing with the notation, we also refer to the density operator as a state itself. So if we do know precisely the state of the system, that means we know the pure state, the vector and the density matrix is just a projection onto that state. Otherwise, we say the state is in a mixed state. So the properties of density operator, it's always normalized to trace 1, just because all of these PJs, they sum up to 1. It is non-negative. and it is Hermitian. So of course, bin Hermitian is already included in positivity, but it's could be stated separately. Okay, so the entropy of the state is sort of the measure of uncertainty about the state. It's given by the trace of rho times log rho. So log rho, you take the log of the PJs. So if you do know the spectral decomposition of your state, the quantum entropy is basically the classical entropy of the probability distribution, PJ. For the binary entropy, when you just have 2p and 1 minus p probability distribution, then it just looks like this. If you do have a quantum system on two parties, like A and B, Alice and Bob here, if the whole state is on both of these systems, then the quantum entropy is called the joint quantum entropy. It's still the same, trace rho log rho, and we can denote it differently depending on what we want to emphasize. Classically, it's interesting that the joint entropy is always greater or equal than the marginal entropies, the entropies of each individual states. However, quantumly, that may not be true. For example, for a pure state on two systems, A and B, so it's a vector on its Samsa product of two Hilbert spaces, the entropy of a pure state, any pure state, is always 0. However, the marginal entropies are equal to each other, and they're not 0. So the marginal entropies, it's the entropy of a state only on the system A here, so that's a partial trace of the projector on this vector psi. So additional properties of the entropy is that it is additive on tensor product states. The subadditivity was proved in 70s, is that the marginal entropies is less or equal than the sum, the joint entropy is less or equal than the sum of marginal ones, and is greater than the difference between them. The strong subadditivity talks about the tripartite states, and it compares the entropy of a tripartite state plus, let's say, the middle state B, and it's less or equal than individual entropies of the states AB and BC. And that was proved by Lieb and Ruskay in 73, and there have been many, many ways to prove the strong subadditivity, different ways since then. Okay, so we have to talk about quantum relative entropy. The quantum relative entropy is sort of measure of the distance between two states. And it's given by the trace function trace rho log rho, which is a negative of the entropy of rho, but now minus log sigma. Okay, it's not necessarily distance, so it's not a distance in a mathematical sense that it satisfies triangle inequality, it does not, but it's a measure of distinguishability between two states. And it's always non-negative, which is not super trivial statement. It could be infinite, especially when the states are orthogonal to each other, then it's actually a pretty good relative entropy because it's easy to distinguish these two states. If it is 0, then it's impossible to distinguish states rho and sigma. The relative entropy is also invariant under unitary operations, which is exactly what we want. The unitary operations are the noiseless quantum channels, so we can reverse its action, and it doesn't matter whether we apply noiseless quantum channel. So the relative entropy is also additive under the tensor products. And the data processing inequality, otherwise known as monotonicity of quantum relative entropy, it says that the relative entropy decreases after the states pass through the same noisy quantum channel, which is given by completely positive trace preserving map. So we're going to talk about that in a second. And in particular, you can take that map as partial trace. And so the inequality becomes the relative entropy between systems on AB is larger or equal than the relative entropy between systems on one of the systems, let's say A. Okay, so we talked about several properties, the strong subadditivity of quantum entropy, there is another property called joint convexity of quantum relative entropy. So if rho and sigma are convex combination with the same probability coefficients of some states rho j and sigma j, then the quantum relative entropy is jointly convex. And then we have two properties, monotonicity under any noisy quantum channel and monotonicity under partial traces. And it's interesting that all of these four properties are equivalent to each other, in a sense that one of them, let's say monotonicity under partial traces, hold for all states if and only if strong subjectivity relation holds for all states. So proving one of them for all states will prove the rest. So it's interesting that, of course, you can go from monotonicity of relative entropy under noisy channels to partial traces, but the other way around, they are equivalent to each other, which is pretty interesting. And that is because of the Stein-Spring factorization theorem, that any noisy channel can be written as a partial trace on a bigger system. So to my system rho, to my state rho, I add additional, let's call environment system in some pure state. Then my noisy channel is going to be the partial trace of a unitary channel on the joint system. So that is why the partial traces is equivalent to any noisy channel. Okay, so this is my new state rho AE. Okay. Okay, so if you want to know more about all these properties, there is a Wikipedia article, Strong Subjectivity of Quantum Entropy, which I wrote with Elliot Lieb and Eric Carlin. All right, so let's talk about the data processing inequality. For any states, this inequality is satisfied, right? This is what we talked about. This is a completely positive trace preserving map, the N. So what does that mean? Completely positive, it means that if you tensor this map with identities on any dimension, it maps positive maps into positive maps. And trace preserving means that the trace of the action is still one. So it maps density operators into density operators, states into states. Okay, so in particular for the bipartite system and the partial trace, the data processing inequality becomes this one. The interesting case is, when do you have the equality? So the equality happens in the data processing inequality if and only if both states can be recovered from the action of this noisy channel perfectly well. So there exists a recovery map called the PATS recovery map, dependent on that channel and the states, of course, that recovers the states n of rho and n of sigma perfectly well. So that means that this channel becomes a noiseless channel for these two particular states. And there is an explicit way to write this recovery map. This is the explicit way, whatever that is. And for the partial trace, it's an easier expression. You just multiply it on both sides by rho A to the negative 1/2 power and multiply on both sides by the joint system, rho AB. And it could be dependent on rho, it could be dependent on sigma. But this particular map, it obviously recovers state rho A, right? So if instead of omega A, you would have here rho A, you would get the state rho AB. So the non-trivial statement is that it recovers sigma state. So if you put here sigma A, that would be a non-trivial statement that it is equal to sigma AB. Okay, so let's talk about different relative entropies. Just like in the classical case, there is a Renyi relative entropy. But in the classical case, it's simple. You just take the coefficients here, p to the power alpha, q to the power 1 minus alpha, and you're done. In the quantum case, it becomes a bit more complicated because rho and sigma, they do not commute with each other. So that is why there are different ways to generalize it to a one parameter family S alpha. This is the simplest way. It's a log of the trace rho to the alpha sigma 1 minus alpha. When alpha goes to 1, the Renyi relative entropy converges to the regular omega k relative entropy. However, as I said, because rho and sigma do not commute, we can write it in a different way. We can write it as interchangeable sigma rho, sigma rho, sigma rho, and so on. So we write it as a sandwich called Renyi relative entropy. But overall, the power, if they do commute, then the power of rho becomes rho to the alpha, and the power of sigma becomes 1 minus alpha. If they do commute, it becomes the same Renyi relative entropy. But quantumly, they're different. And again, here, so this is the minimal quantum relative entropy in the sense that for any alpha, the value of the sandwich relative entropy is always less or equal than the value of the Renyi relative entropy. So this is a non-trivial statement which is proved using Araki-Lipth-Thirin inequality, which states that the trace of the power of the matrix A, B, A star, you can separate A's and B's. It's less or equal than the trace of the product A star A to the power alpha times B to the power alpha. So this is how you separate A's and B's. And this is exactly what we need here. We need to separate sigma and alphas into different terms. Okay. And even more general class of Renyi relative entropies is a two-parameter family called alpha and z. So what if, let me put the different slide here. So the previous slide, what if instead of the alpha on the bottom here, I have a different parameter, right, z? So again, if rho and sigma commute, it just becomes the same Renyi relative entropy. But if they do not commute, it gives you a different family. So when z is equal to 1, right, when this is 1, this just becomes the Renyi relative entropy. It's just going to be rho to the alpha, sigma to the power 1 minus alpha. And when z is equal to alpha, this is exactly what we just had. It is a sandwich Renyi relative entropy. Okay, and a more general, however, it's a different generalization of quantum relative entropy is called the F divergence or quasi-relative entropy. It is based on the operator convex function. We have some normalization of it. F of 1 is 0. And the F divergence is defined as the trace of the function of the modular operator, which I'm going to define in a second, applied to the state rho. So the modular operator, what it does, it multiplies an operator to the left and to the right, right? It's multiplied by A to the left and by B inverse to the right. But now I take the function of this operator and apply it to rho. This is going to be the F divergence. There is an easier way to calculate it if you know the spectral decompositions of your states. So if rho has the following spectral decomposition and sigma has another one, then the quasi-relative entropy can be calculated straightforward from this expression. It's lambda j's from the rho's function of the quotient here for any coefficient k and j, and the overlap between two states. So when the function is a logarithm, then it is a regular relative entropy. It's just the relative entropy as we talked about. If the function is the power function, then it gives what's called the Tsali's function. It's the expression that we've seen in the Renyi relative entropy, right? Just without the log. And it's called the Tsali's Q entropy. And again, if the function is the power, it gives rise to the Renyi relative entropy, but you have to additionally apply the logarithm here to the quasi-relative entropy. However, the quasi-relative entropy is, you cannot define the sandwich relative entropy using quasi-relative entropy. So these are two different generalizations. And there are many, many other ways to generalize the relative entropy. There's whole entropy zoo. You can find this picture, I think, on Wikipedia as well. and all of these different connections between these entropies. But we're going to just talk about the ones I introduced. So let's go back to the data processing inequality. This is the data processing inequality from the beginning by Patz in 85. Oh, in 85, it was proved for the quasi-relative entropy, for the F divergence. For any convex function, the data processing inequality was proved. So this takes care of the Renyi relative entropy as well, because the Renyi relative entropy and the Tsallis ones, they are particular cases of the F divergence. However, for the sandwiched relative entropy, this becomes more tricky, and it was proved in 2 papers for different parameters that it also satisfies. For these parameters, when alpha is less than 1/2, and the sandwich entropy is still defined for this parameter, but for that parameter, it doesn't satisfy the data processing inequality. There are counterexamples for any alpha. The proof of the data processing depends on the joint convexity of this map, of the part of the sandwiched definition there. And this map is jointly concave for alpha between 1/2 and 1, and convex for alpha greater than 1. That's why you have the proper inequality when you multiply by 1 minus alpha. So to prove the joint convexity of that map, what was done is the following representation, where you can separate rho and sigma. So the joint convexity, right, it's a little bit harder to prove than just convexity of the map when you have only one parameter, rho or sigma. For example, the first term over here, I mean, it's linear, so obviously convex. The second term here, this is also a little bit tricky. However, we do not have a rho here, so it becomes an easier problem. So let's look at the second term. So the second term is in the form k star a to the power p k to the power 1 over p. And this one was proved by a series of papers, Upstein, Ando, and Carlin and Lieb, provided a different alternative proof that this map is concave for p between -1 and 1. And it could be generalized to different powers here, p, and instead of 1 over p, you can take a second parameter family, let's say some s, and ask the question, when is this trace function gamma is concave or convex? And here's the result for different parameter, when is this function concave and convex? In each of these cases was proved separately or several times over by various people, by Upstein, Carlin, and Lieb. They provided alternative proof, and here, second one by here, and the third one, Carlin and Lieb again. That's interesting that these conditions are also necessary in the sense that if my function gamma is concave, for example, for any invertible matrices and 2 by 2 matrices, then it only happens in this case. And I forgot the S here parameter as well. The S also satisfies this one. And it is convex for 4 by 4 matrices A if either the second part holds or the third part holds. So only for these parameters. So of course, this is good that the matrices in the first case are 2 by 2. You can easily generalize it to 3 by 3 because that's a particular case. However, we do not know what happens for 2 by 2 and 3 by 3 matrices in the convex case. Okay, now, so that was the sandwich relative entropy, right? Now let's talk about the alpha Z Renyi relative entropy. And it's very recently, in 2020, Zhang proved that it satisfies the data processing inequality if and only if the parameters satisfy these 3 conditions. And I'm going to draw a picture of these conditions when that happens. The proof depends on the convexity of the following, joint convexity of the following function. So it's b to the power some power q over 2, a to the power p, b to the power q over 2, and another power s. So you have 3 parameter family here. And that is true because even before in 2013, Carl and Frank and Lieb, they showed that alpha Z family is monotone under noisy quantum channels if and only if this function is jointly convex for alpha larger than 1 and concave for alpha less than 1. And this is pretty interesting, that monotonicity is equivalent to convexity. And why is that? So remember, the alpha Z relative entropy was defined as the log of trace of this function, right? So this is log of exactly the psi function with the proper P, Q, and S. And P, Q, and S are defined here on the top of the screen. P is alpha over Z, Q, and S. So the alpha Z relative entropy is log of the function psi. And I want to prove the monotonicity of the alpha Z relative entropy. So the statement is that monotonicity of alpha Z relative entropy is equivalent to the joint convexity or concavity of psi. So because this is a log of psi, the monotonicity is equivalent to the monotonicity of psi. So again, the statement is that psi is monotone if and only if it is convex or concave. So how do we do this? Let's assume it is monotone, right? Then I need to prove the convexity. What we're going to do, we're going to go to the higher dimension. We're proving convexity, so that means we have 2 states, rho 1, rho 2, for rho with weights here, lambda and 1 minus lambda, and for sigma, we have sigma 1, sigma 2 with the similar weights, lambda and 1 minus lambda. So we go to the larger space and create a single state rho out of these 2 and sigma out of these 2. Now the map that I'm going to consider as a noisy quantum channel, it's going to add the diagonal terms a plus d and a plus d, that's it, and we just ignore all diagonal terms here. So the monotonicity of psi under this map, it just implies convexity straightforward. Okay, so when you apply psi to this map, it's going to be exactly the convex combination of rhos and sigmas. Okay, so that was straightforward. The other way, if I know the joint convexity of psi, how do I show the monotonicity of psi? So what do I need to show? I need to show that it is monotone under noisy CPTP maps, right? Completely positive trace preserving. But these maps, remember, as I said before, it could be written as a partial trace on the larger system and unitary transformation there. So if I add here an identity, normalized identity to this map, I can also write it as the normalized Haar measure on the group of all unitaries. And from here, we get the monotonicity. So the psi on the processed states rho and sigma is going to be the psi of processed states tensor identities. I don't care whether I tensor with identities because the trace of the identity, normalized identity, is 1. And so by convexity, psi of the processed states by convexity is less or equal than the integral of psi of all of these states. But these states are pretty easy because we have a unitary transformations on them, and the unitary transformation doesn't change my psi. So this is just going to be psi, rho, and sigma. Okay, so we talked about the function psi, right? Here's a little bit generalization of this map. If I add additional operators k inside the trace function, right? So when k is identity is the function psi that we just talked about. But here we can consider it for any operators k. The interesting result by Carl and Frank and Lieb said that the following are equivalent about this function, is that it is jointly convex for all k on any dimensions, right? This is equivalent to the statement that it is jointly convex for all unitary operators. And It is equivalent to the statement that it is jointly convex when K is equal to identity. Also equivalent to the statement that if I take the similar states, or the similar operators A, and it is convex for all K. Not jointly convex, but just convex in A. And again, it's equivalent when you take all unitary Ks. So some of these statements are pretty straightforward, right? If I know it's jointly convex for all K, then I can get all of these statements straightforward as a partial cases. Also, from unitary, you can take identity. From any K, you can take the unitary. So these implications are also trivial. The interesting ones are the other way around. So if I have the joint convexity when K is equal to identity, why do I have the convexity for unitaries? And it turns out that you have the expression inside this psi, right? K star A to the pk. And that can be written as the power of K star AK when K is a unitary. So you can absorb the K inside the A. And that is why if you have the statement for K equals identity, you have the statement for the unitaries because you can absorb it inside the operator A. The implication from unitary to any K. This is a bit non-trivial. And here how it goes. So take the operator K and consider its polar decomposition, right? Then we're going to create a bigger matrix. So again, we're going to the bigger space. We're creating a larger matrix with diagonals K and some of these operators W identity minus K squared. So this is a unitary. If you check it, this is a unitary. And on this space, we're going to consider new operators A and B. A is my matrix A, and here I'm just going to add the T's on the diagonal. And B is a B inserted into the larger space. Then the expression that I'm interested in, A to the power Q over 2, K star B to the P, and all of this, this is the limit when T goes to infinity of the larger matrix. The same expression though, but on the larger space. So when Q is less than 0, this T goes to infinity. When Q is larger, T goes to 0. And so when I take the trace of this, so the psi is going to be equal to the psi to the limit of the psi's. And if I have the joint convexity there, I will have the joint convexity in a smaller space as well. And the implication 5 to 3, which means if it is convex for all unitary K when A is equal to B, it is jointly convex when K is, let's say, is 1, but I have different matrices A and B. So in this case, we're going to take the bigger matrix A, which is a composite of matrices A and B on the diagonal, and K to be the block identity, but on the off-diagonal elements. So this is the block identity matrices. And that's it. So from there, you get the straightforward application. So let's go back to the theorem of Zhang, who proved that alpha Z relative entropy satisfies the data processing inequality. To show that, as we've seen, it is enough to work with the joint convexity of the function psi. And he showed that this map psi is jointly concave, convex under these parameters. And I think, yes, so under these parameters, in yellow region it is convex, in green region it is concave. And this is if and only if statement, so this is it, only under these parameters. Okay, so it's interesting again that even before we had the necessity of this statement, we knew that if psi is jointly concave, then the parameters are exactly as we've seen. And if it is jointly convex, again, the parameters are exactly as we've seen. The non-trivial statements were the other way around. Okay, so the key of the proof were the expressions, again, on how to separate the operators x and y. So we're proving the joint convexity, and to prove that it's easier to separate the operators x and y using these variational expressions. Okay, so let's talk about the equality then in the data processing inequality. This is, as I've said before, for the regular relative entropy, we have equality if and only if there exists a recovery map that recovers both of the states perfectly well. So for the partial trace, this is the map, and the non-trivial statement is that it recovers state sigma if I write it dependent on the state row. So equivalently, if I just place all the states on the joint system 1, 2 on the right and marginal states on the left, this is a non-trivial statement I have. I have some state on the system 1, tensor identity on the system 2. This must be equal to the joint state on systems 1 and 2 like this. So that's a non-trivial statement. And for the Renyi relative entropy, a similar expression is satisfied. So if we do have an equality in the data processing inequality, this happens if and only if there exists a recovery. So the n star map applied to the process state sigma to the power minus z and the process state rho to the power z recovers the sigma to the minus z and rho to the z. So you can place all the rows on one side, apply the power, and you can have the recovery map. So it actually holds for any quasi-relative entropies, and that we have the equality if and only if the states satisfy. So this is for the partial traces. Apply the partial trace here. This is going to be sigma 1 to the z, rho 1 to the minus z is equal to sigma and rho on the systems 1 and 2. Okay, so for the sandwich relative entropy, even before that in 2017, for different parameters, it was proved that the sandwich Renyi relative entropy saturates the data processing inequality if and only if this whole big expression holds. But this is very similar to what we had before, right? Just different powers here. Now you have to work with the sandwiched part. So one can ask the same question, what happens in the alpha z, right? So probably I'm going to have to change some of these alphas to the power z. So the question is, it saturates the data processing inequality if and only if what statement holds. And Zheng in 2020, he proved that the following holds even a more big expression. So this x, this is my left-hand side, is equal to n star applied to this whole part. And it just, yeah, it's a big expression. However, the proof of this uses convexity of this function psi, right, that we talked about. There is another necessary condition that my student Sarah tried to explore. So she showed that this expression, this condition holds, but this expression depends on the convexity of the following functional. So this functional, remember we had the psi, right? And the psi was in this form. It was a to some power, k, b to some power. But what if I place my k not between a and b, but outside of this? So it's going to be k on the left, k on the right, and my expression a inside, right? So it looks very similar. So why would there be much of a problem here? However, it proved much harder to investigate convexity than the psi. So the question is, for which parameters this new function lambda is convex for k and b, not m, b. Or again, instead of the, oh, sorry, what is that? Yes. And again, so here we have parameters p and 1 over p. Again, I can add another parameter s as p and the whole power to the s, right? So let's investigate this new function lambda. And this is sort of like similar to what we already had, right? We had the k's on the outside when we considered gamma function, k, a to the power p, k. So if I don't have my b, if the operator b is identity, this is the gamma function, right? So this is a generalization. The lambda is a generalization of all the gammas and psi's. Just as separate results but related were in old results that the operator A, B inverse A, the operator itself, it's jointly convex. So it's jointly operator convex on positive definite operators. So the question was asked by Eric, Carlin, and Lieb, what happens if I add some different powers here? Would it be still jointly operator convex for some parameters? And this is related to the convexity of the trace function. Yeah? So there is a difference jointly operator convex, and taking a trace, it just becomes a function. So in 15, Eric, Carlin, Frank, and Lieb, they showed that the function, the trace function, is convex, then the function f is operator convex. So in fact, the convexity of the trace function is a stronger statement than the operator convexity, which is pretty fun because one would think that joint operator convexity is a more stronger statement, but in fact, the trace function convexity is a stronger statement here than the operator convexity. Okay, and they proved that the map a to the power q, b, p, a to the power q is jointly convex if and only if q is equal to 2. So we don't have the power here, it's just a times b to the p, a. And this is a very trivial expression. And the map is never jointly operator concave. So in fact, this is not an interesting generalization, turns out, because it jointly convex only in the most trivial case. And from here, we get that the trace function is never concave and it is convex if and only if, again, there is no power for A. Okay, the counterexample that it doesn't hold is based on the result that the map x to the r, y, x to the r is not operator convex on positive definite matrices. So again, the map x to the operator x to the r, y, x to the r is not operator convex. Okay, so when we started working with this lambda, we made a conjecture, well, this is probably never concave, just like the function f, and it is convex only in the trivial case when q is equal to 2, so there's no power for a, and s is equal to 1. Okay. Just a separate result. So we've been talking about convexity in the operator A, right? Or joint convexity in A and B. But what if I look at this at the function K to this function, right? And Lieb in 73, he showed that this function K to the function psi is convex in K. Okay, so let's quickly recap what functions we have. We have a function lambda that we're interested in, and we have the gamma, which is just on A. It's k star ap to the k. This is when this operator m is identity. Psi depends on A and B and the fixed operator k. So this is when A and k's in lambdas are switched sides. And then we have the omega function, which is a trace of the three operators. So we have the relation when m is identity, this is the function gamma, lambda is a function gamma. When lambda has k as identity and psi has k as identity, then, well, the k is identity and the parameter one, then they're also equal to each other, and lambda can also be reduced to the omega on the proper parameters here. Okay, so we do know that gamma is convex for a large range of parameters P and S, right? We also, so another question, what happens if I perturb this identity just a little bit, right? So when my M is identity, the lambda is convex for a pretty good range of P and S. So if I perturb my identity here just a little bit, would I lose convexity or would it stay for some time? Same question for psi. It is convex for a large range. So if I perturb this first operator from identity a little bit, would it still hold the convexity or not? Okay, so this is what we proved last year, that the function lambda as a function of A is convex if and only if the parameter P is 2, so there's no power for A, and S is not 1. S is larger or equal than 1/2. So it's a pretty good range. However, it is never concave, just as expected. So when P is equal to 2, and for any positive S, this is easy to prove that it is convex from function gamma, because I can absorb the parameter M, the operator M here, inside A and inside K. Okay, and get the identity, because when there is an identity on the second operator, this is my function gamma. And all we did for this M, we just absorbed it into A and into K. But that holds only for parameter P equals 2, when there is no power for A. So that is convex, because gamma is convex for S larger than 1/2 in this case. And the other way, that was a non-trivial statement, which I'm going to show how to prove quickly. The interesting questions that I asked, right? I asked whether if I perturb my operator M or K from identity a little bit, would I lose convexity? And in fact, yes, I would lose convexity all the time. So even if I perturb just a little bit, I would lose convexity and concavity immediately. So this is the stability of convexity of gamma. There exists the K invertible operator K and the positive definite M that is very close to identity, however you like close, such that lambda is no longer concave or convex. And the key points is that we do construct explicit operators M and K that would lose this convexity. Okay, so this K, because I need it to be invertible, I need to take some parameter K here, which is very small, but proving it to 0, that would be enough, and then taking limit K goes to 0 would give me the same inequality. So proving that it is not convex or concave, choose any we're going to choose the operator A1 in the form AB, which we're going to choose later, and A2 as identity plus X times the diagonal elements here. Well, now we'll consider the expression in the convexity of lambda, right? So it's lambda of A1 plus lambda of A2 minus lambda of A, which is the A1 plus A2 divided by 2. So it's exactly the expression in the convexity. Now, after some calculations, I can rewrite this function as the following one. So this is 2 times S times T times X, right? These are the parameters that I had, times the function, and this is the function which depends on parameter P and the B inside the A1 that we have to choose. So this OX, it just goes to as X. It converges as X to 0. So this function GP at 0, it is equal to this expression, which is convex in P. So it is convex in P and equals 0 at P equals 0 and 2. So that means I can choose some B, which is larger than 0, such that GP of B is not equal to 0. So I can go away from 0. And well, let's fix that B. This is the B that I want for my operator A1. And then we're going to choose X, which is also in the operator A2, right? So this is something we can choose. such that this function is either positive or negative depending on whether you're disproving convexity or concavity of. Okay, so that was the stability of function gamma. The stability of convexity of psi is very similar. So remember that we had lambda is equal to psi when I have the identity function here. So, and this psi is jointly concave or convex for non-trivial parameter ranges. So the question again, if I perturb this identity, so my k a little bit, well, it turns out that even if you perturb a little bit, you would lose concavity and convexity for these parameter ranges as well. And this is actually straightforward application from the stability of gamma, because this is my lambda, right? I'm just rewriting what my lambda is. It's this trace function. But I can switch m's and k's with the following formula. When I use the following formula, k, m star m, and you can switch it with m, k star, k star by just cyclicity of trace. And what we do, we're just gonna take the new k tilde and m tilde such that m tilde is the k star, and m over here on the right hand side is the previous k tilde star. So just as in the previous theorem. And so we just play around with the switch in order of m and k and show that the function is never concave or convex from the previous result. Okay, so in 21, Zhang also considered the similar function lambda to ours, and he also proved that it is not convex or concave, but for smaller parameter ranges. Our result, we showed if and only if statements. But he also considered a different function, the function on 3 operators, A and B and C, in a similar form, and he showed that it is jointly convex for the listed parameter ranges. And the range is optimal, so again, there is a necessity condition that if the map is jointly convex, then the parameters are exactly as above. All right, and let me finish here. Thank you.
Thank you very much. Okay, Mr. Audience, do you have any questions for our speaker, Dr. Vershynina?
I have one quick question. That picture with the entropy zoo, where did you say it's located?
Where is it located? Let me see. I think I had some reference here to that picture. It's in some. I was hoping it's on the Wikipedia, but let me see. No guarantee of correctness, completeness, no liability. Entropy zoo. Okay, so here's the person who wrote it, Philip Effaced.
Okay.
I think it's in one of his papers. However, I think it's posted somewhere on Wikipedia or Quanticky. It's a quantum Wikipedia.
Yeah, you just Google it, Sergey.
Yeah, I will. I wonder if Boltzmann turns in his grave every time new species are introduced to this zoo. You know his gravestone in Vienna, right? Obviously. Yeah. All right. Nice talk otherwise, everybody. Thank you.
Yeah. Convexity, is one of the most difficult part of this topic. Yeah. So, all right. Do you have anything else for our speaker?
Thank you for the interesting talk, Anna.
Thank you.
Yeah. So, if not, let's thank our speaker, again for her very interesting talk. Yeah.
Thank you.
Yeah. Thank you very much, Anna. And so this semester we have like a bi-weekly seminar, and after 2 weeks we have a talk from delivered by Sejong Kim, from Korea, and he's also working on Kachuming and Bourret's position, distance, and related questions. So I hope to see you in 2 weeks.
All right.
Yeah, thank you.
Bye.
All right. Thank you. Bye.
Bye,
Bye.
everybody.